Welcome to our exploration of EASA Module 03, Electrical Fundamentals.
Right, the bedrock for anyone, gunning for their B1 or B2 maintenance certification.
Exactly. We're moving from the behavior of subatomic particles all the way to the heavy-duty systems that actually get those turbines spinning.
And the mission today is really to bridge that gap between textbook physics and what you're actually going to see on the hangar floor.
Because it's not just magic in the wires, right?
No, not at all. It's a series of highly predictable laws. When you look at an aircraft's electrical system, you're really just looking at matter in motion.
But to understand that motion, we have to talk about the free electrons.
Yeah, the ones in the valence shells of your conductors.
No.
In aviation, we rely on materials like copper and silver because those outermost electrons are loosely bound.
Meaning they're ready to move the second you apply a little pressure.
Exactly.
But that movement is, it's often totally misunderstood. You hear people say electricity moves at the speed of light.
Well, the effect does, sure. But the individual electrons, they're actually quite slow. That's drift velocity.
Right. They're constantly bumping into atoms.
The best way to visualize it for the exams is a long tube packed completely tight with steel balls.
You push one in at your end,
and another pops out the far end instantly. So the effect is immediate, even if that individual ball is taking its time getting down the tube.
That distinction makes a lot of sense, especially when we start looking at uncontrolled potential, like static electricity.
Oh, absolutely. Out in your environment, static isn't just a carpet shock. It is a high-stakes hazard.
Because friction builds up a charge.
Yeah.
Fuel flowing through a line, air rushing over the fuselage.
And if you're handling a sensitive circuit card without being grounded, the law of attraction kicks in. You get electrostatic discharge, or ESD.
And you might not even feel the spark.
But you've just caused breakdown damage to a solid-state component. That's exactly why you always see grounding straps and protective caps in a professional shop.
So since static is basically uncontrolled pressure, we need to talk about how we measure and direct the controlled stuff.
Voltage.
Right, the electromotive force, or EMF. I was like the water tank analogy.
Two interconnected tanks. The water only moves if there's a difference in pressure between them.
And in your circuits, voltage is that potential difference pushing the electrons through the wire.
Yeah.
But we have to keep our heads straight on conventional flow versus electron flow.
Yeah, Benjamin Franklin's old theory, he said positive to negative, which we still use for conventional circuit analysis.
But the physical reality inside the wire is that those electrons are moving from the negative source toward the positive.
Precisely. And where you get that electrical pressure from really depends on the system. On a standard airframe, there are 6 primary methods of production.
You've got pressure, like piezoelectric crystals in your sensors, and chemical energy in batteries.
There's also thermal energy via the Seebeck effect. That's why your EGT sensors are so rugged and self-powering in high heat zones.
Then you have light, friction, and the heavy lifter.
Magnetism combined with motion. Your generators.
Speaking of chemical production, picking the right battery is a massive part of the maintenance routine. Usually you're dealing with lead acid or nickel cadmium.
Right. With a lead-acid battery, you use a hydrometer to check the specific gravity of the electrolyte. That tells you the state of charge.
But NiCads are a totally different beast.
They're fantastic for high-cycle demands, but you have to watch out for voltage depression.
The memory effect.
Exactly. If they aren't maintained through proper deep cycling, they lose capacity.
Which is why sealed lead-acid, or SLA batteries, have become so popular for standby power now.
They're essentially fit and forget compared to NiCads. Simpler maintenance, built-in test circuits.
Okay, so regardless of the source, once that current is flowing, you're governed by the laws of the circuit. Ohm's law and Kirchhoff's laws.
Your primary troubleshooting tools. Say you've got a dim landing light.
Ohm's law tells you that if the source voltage is constant and the light is dimming, meaning the current dropped, your resistance had to have increased.
Likely due to a corroded connection somewhere.
And Kirchhoff's voltage law is just as practical.
In a series circuit, the sum of all your voltage drops has to equal your total source voltage.
So if you have a 24-volt system and your components are only dropping 20 volts total, you know you have an unwanted resistance somewhere in that line.
It's all a closed loop, from the valence shell of a copper atom all the way to a heavy turbine starter.
You really do get a framework to see the aircraft as a balanced system of energy.
It changes how you look at the machine.
It really does. Well, before we wrap up this exploration, here is something to mull over. We know a true vacuum has no electrons of its own to carry a charge.
Right, it's completely empty.
Yet physics states it is an ideal conductor if you actually inject electrons into it. Why would a complete void be a more perfect path for energy than a wire made of solid gold?
That is definitely something to think about.
Until next time.